Welcome back, folks. So, last time we talked about Kepler's laws and how most of astronomy actually depends upon Kepler's laws, but we can actually utilize that when we're looking for aliens as well. One of the things we talked about was how if I know the orbital period of the planet and I know the mass of the star, then I can figure out the distance of the planet from the star. So, what we're going to talk about today is the technique that will allow us to actually do that. We're going to get the orbital period and then using Kepler's laws, we're able to get the distance from the planet to the star. But we can also get something else. And I mentioned this in the very first class, but using something called the transit method. Whenever the planet passes in front of the star, it's going to block some of the light. And that's going to make the light from the star dim. The bigger the star, the more light is going to be blocked. I'm sorry, the bigger the planet, the more light is going to be blocked from the star. So this would allow us to figure out the size of the planet. So that will tell us, are we working with a terrestrial world that we might find aliens on, or are we talking about a gas giant or something like that? So what I'm going to teach you today is the technique that we actually use at GCC North Observatory. And this is what we've used to observe actual alien planets going around their star. So everything you're doing here is real. And if you understand it, and it's not that hard to understand, you'd actually be able to do this yourself. Let's get started. All right, so as I said, we're talking about the transit method, and transit just means to pass in front of. That's all, just to cross in front of. And what you're looking at here is some actual data of an actual alien planet moving around in front of its star. Now, this, of course, is just a drawing, but it's showing you what's happening here. And you see right here, I've got 100% of the light, roughly. There's always going to be some noise in your data. That doesn't mean that the star is actually changing brightness. It just means your receiver, your telescope, has some noise in the variation of light. It could be clouds moving in front, it could be changes in the atmosphere, things like that. There's always going to be there. And it's one of the challenges of doing this kind of astronomy. But overall, you can see that it's basically 100% right here. Then, just when the planet starts to pass in front of the star, it blocks that light, and the light from the star dims. When the planet moves off of the star, now it comes back up and we're back to 100%. And in a nutshell, that's exactly what we're doing. We're going to watch several of these. Now, the depth of the curve then, this is called a light curve. The depth of the light curve is going to tell me how big the planet is. What we usually do is we observe several of these light curves. And in your final project, you're going to have to see at least two dips. And so you'll see a dip and then you'll see another dip. The time between those dips, that's one orbit. So from the time from one dip to the next dip is going to be one orbit. And so that gives you the orbital period, and from that you can get the distance. So let's go through the details here. So you tell me, based on what we've talked about, what would happen to the size of the dip if the planet were larger? Think about it. We're going to be blocking more of the light. And so it's going to get a deeper curve here. And this is exactly what happens when we have an eclipse. The moon, as seen from Earth, seems to be coincidentally roughly the same size as the sun. Now, obviously, it's not, but the sun is a long, long, long way away. And so the sun seems small and the moon seems to be exactly the same size. So when they pass in front of each other, when the moon passes in front of the sun, then it blocks out the light and it gets dark. Now, in this case, the star is very far away. And so, for all intents and purposes, the planet is on top of the star as far as we can tell from here, because that tiny distance compared to the distance from us to the star is nothing. So what we see then is actually directly the size of the planet. It doesn't really matter how far away the planet is from the star, because again, there's just basically no difference when you're comparing to the distance from us to the Earth. So when we take a timing light curve, and this is one of the detectors that we've talked about before. So right here, you see we've got 100% of the brightness. And yeah, there's noise. That's normal. That doesn't tell you anything about what's going on. There's always going to be noise. Our observatory was designed specifically to try to minimize that noise, because the noise of just a truck passing by can vibrate your telescope to the point where all the whole dips are completely washed out. So instead of these tight little variations here, you've got variations that go all the way across like this, and you can't see the planet. So we designed the observatory with huge concrete caissons. They're about, maybe probably about 4 or 5 feet across. And then they go down into the ground. And then the piers that support the telescopes are mounted to those caissons. Those caissons absorb vibration. And so that keeps the telescope from shaking. So the whole system cost about $50,000. People go up to the observatory and they're like, where's the magic? Where's the good stuff? Well, it's because it's mostly all underground, Because having that vibration isolation system is what makes it possible for us to do this kind of work. So whenever the planet's not in front of the star, we get 100% of the light, roughly. Then whenever the planet passes in front of the star, we get this dip. Now you'll notice that these dips look a lot sharper than what we saw on the previous screen up here. Well, that's just because of the scale. Here, instead of showing, several hours, I'm showing each one of these things as a day. And so we've just basically zoomed out, and so the pieces get compressed so that I can see individual dips. Each time the planet passes in front of the star, we get one of these dips. So the percentage blocked here, you can read right off the screen right here. So this is 99.970. The next mark is 971, 972, 973, 974, 975. And so the total brightness drop, the lowest brightness, is 99.973%. Okay, that's the first part. That gives us the number that we're actually going to need, but that's what you're going to read off the graph. You need to be real careful about how to read these. Notice, look at each one. Usually I'll tell you how much each tick mark is. In this case, each tick mark is 0.001. Sometimes it's 0.002. Sometimes it's 0.004. So you want to be real careful about that when you're reading off the scale. So the size of the planet then is determined, we can measure that by measuring the depth of the dip here. So let's take a look at that. So now the lowest brightness that I read here was 99.973. Okay, the percent drop is what I need. And so that's 100 minus the lowest brightness. And this is where I see a lot of students go wrong, is they'll put into the size formula, this is the tool that allows you to calculate the planet radius. They'll put 99.973. That's wrong. That percent drop should always be a tiny, tiny number. If it's not a tiny, tiny number, you're doing something wrong. Figure it out. So 100 minus, in this case, 99.973 gives you what, 0.027? So that's what would go right here, 0.027. Divided by 100, raised to the 0.5 power. You could also raise it to the 1/2. 1/2 is 0.5, and you'll see that in some of the equations. If you do that, make sure you put that 1/2 in parentheses so you'll get the wrong answer. That's why I don't like to use that. I prefer to just use 0.5. For those who are maybe a little more comfortable with the math, raising to the 0.5 power is the same as taking the square root. So you could also take the square root of what's there. You do you. I find most students find it easiest to do it this way. 0.027 in this case, divide by 100, hit equals, raise to the 0.5 equals, times the radius of the star. Well, where do I get the radius of the star? Well, you figured that out before. Remember that you need to reference your earlier tools. These tools don't work independently. They always use the previous stuff. So if you've forgotten how to find the size of the star, you just flip back through your class notes and you find finding size, and it'll show you step by step through the procedure of how to find the size of the star. So this is the size of the star in solar radii. So if the star is twice the size of the sun, then this would be 2. If it's 1.8 times the size of the sun, then this would be 1.8. So 0.0273, I think we said, divide by 100 equals, raised to the 0.5 equals, times 1.8, whatever it is, equals, times 109 equals. You'll find it easier to hit equals after each one than it is to type it all in one go, because you're less likely to make a mistake that way. Now this gives you the radius of the planet in Earth radii. So just like with solar radii, if I get that the planet is 1.4 Earth radii, it's 1.4 times the size of the Earth. If it's 0.5, it's half the size of the Earth. If it's 3, it's 3 times the size of the Earth. Sometimes, occasionally, you will need to figure out the size in Jupiter radii, particularly if we're talking about gas giants. You just take your radius that you got here in Earth radii and multiply by 0.0892. This is the ratio of Jupiter to Earth in radii. So really simple. You just multiply by 0.0892, and this will give it to you in Jupiter radii. All right. So let's do a sample. Look in your class notes, and you'll see the notes here. So this is on the back of page 2. So suppose we have a star radius that's 1.25 solar radii. I'm giving it to you this time. In your project and in most of your work, you're going to actually figure this out yourself. You'll have figured it out based on previous things. But given the length, I don't want you to spend too much time on the homework. So for this section, I'm going ahead and giving it to you. But make sure that you know how to calculate that if you need to. All right, so in this case, we're saying that the star is one and a quarter times the size of the sun. And we got a brightness drop of 99.973. So the next step then is to take the brightness drop. It's 100 minus 99.973, and that's 0.027. All right, now you pick up with this and figure out the size of the planet. I want you to pause the video. This is all that we've done up to this point. I want you to pause the video and then look at the tool that's printed at the top of page 2. And I want you to figure out the radius of this planet. Pause the video, do that, and then come back. Okay, ready to go? So if we plug this in then, here's the tool. I'm going to take 0.027. Now, some students, when they see this percent, they're like, oh, wait a minute, do I have to like move the decimal 2 places one way or the other? No. In this case, percent is just a unit. So just like you would never put units in your calculator, you never put percentage. You wouldn't put meters in your calculator. You wouldn't type METERS. Same thing. You don't put the percent in your calculator. You just leave it as 0.027. Done. 0.027 divided by 100 equals, raised to the 0.5, equals, times the star radius that we were given in this case. But in your own work, you're probably going to have to figure it out yourself. This is where a spreadsheet comes in handy. So times 1.25 times 109 gives 2.24 Earth radii. Did you get the same thing? So 2.24, this means this is a little over twice the size of Earth. So this is a super Earth. And we've actually found planets that are exactly like this. Now, if we needed it in Jupiter radii, always look at the problem. See what units it's calling for. It's not going to just say, hey, dummy, go put this in Jupiter radii. No, you're going to look and it's going to have a blank and it's going to say RJ. And if you forget to see that, if you forget to read that, you're going to put in the number in Earth radii, and well, you're going to get it wrong because you are wrong. Okay, so make sure that you're looking at the units to figure out what you need. So 2.24 Earth radii times 0.0892 says that this is 0.2 Jupiter radii. So this is 20%, 2/10 the size, about 1/5 the size of Jupiter. Okay. Does that make sense? If you're not getting the same answer, go back through and work it out. If you still can't figure it out, come to Live Help and I'll help you. All right, so the next thing that we get the size of the planet from the dip. I can get the orbital period by the number of days between the dip. And this is actually pretty easy. All you got to do is you read off, pick any two. It doesn't matter which one. Don't just read off this number here. Yeah, on our graphs, we generally started at 0. That's just because of the spreadsheet we use to make these. However, in Smart Sparrow and in your projects, that won't be guaranteed. So what you always want to do, you need 2 dips. That's when it goes around the planet, around in front of the star the first time, until it comes around to the star in the second time. So all you need to do is read off the days for this one, read off the days for this one, subtract them. That's the orbital period in days. So we're going to need, in order to do this, then we're going to use Kepler's third law that we just talked about. So A, there's a bunch of different terms for that. They all mean the same thing. Remember, A is the semi-major axis. It's the distance from the planet to the star. It's the orbital radius. All of those things mean exactly the same thing. Don't get confused. What units do we measure A in? You remember? If you're not sure, you might want to go back and look. You never have to memorize the equations, but you do have to know how to use them. And that means you need to know the units. So A is measured in AU, astronomical units. So 1 AU is the distance from the Earth to the Sun. 2 AU would be twice the distance. Mars, for example, is at 1.5 AU. Venus is about 0.7 AU, somewhere in there. Okay. So M is the mass of the star, the mass of the central object. So that's always in solar masses. So how do I get that? Well, if you don't remember, you go back through your class notes and you find finding mass and you figure out the mass. And we get that from the luminosity of the star. So if you don't remember how to find the luminosity, then you go back to that tool and you find the luminosity of the star. So look through, this would be in the star classes page, shows you how to find the mass of a main sequence star. So the star classes, microtask, the class notes there, will show you how to find the mass of a main sequence star if you know the luminosity. What if it's not a main sequence star? Then it's dead to you. If it's not a main sequence star, then if there were any habitable worlds going around that star, they're dead now. So there's no point in worrying about it. Just don't spend any time on it at all. So we are strictly talking about main sequence stars at this point. All right, so you found the luminosity. You've used that in the star classes page to find the star mass. That goes right here. So the only thing I need then is the orbital period. So we get that orbital period then from this, but it's in days. So don't forget, you need to convert that to years. It's a lot of steps to think about. And so this is why it's a good idea to set this up in a spreadsheet so that you're just, going straight across and it'll actually do all the work for you. You could type in the period in days and boom, it's actually gone ahead and calculated the major axis for you. Let's do a sample. I think that'll help you out a whole lot. So let's suppose that from the star classes page, we decided, okay, yes, this is a main sequence star, and I know its luminosity. And from that luminosity, we calculated that the mass of the star was 1.36 solar masses. I'm giving it to you this time. Most of the time, in your project, you're going to have to find that out for yourself. So, and if you're curious where we are, we're about 2/3 of the way down the page, at page 2. All right. So the orbital period from the transit-like curve we decided was 60 days. Let me go back up to the curve here. So I've got about 120 days, and you would want to read that off a little more precisely. But I've got about 120 days and about 60 days here. So 120 minus 60 is 60. You could use any of these. So this is 300 days. This is about 240 days. 300 minus 240, also 60. So it doesn't matter which two. Yes, it's a coincidence that we've started it off at 0, and you don't want to get in the habit, though, of just saying, oh, that one's at 60, I'm good, because that's not going to work a lot of times. So just pick 2 of them, subtract them. That's in days. All right, so we got 60 days. So we need to convert that to years. Well, how many days are in a year? 365. And you can do 365.25, that's fine. But remember, we're only keeping 3 significant digits. So why waste your time? So you take your 60, divide by 365. So you just pick up your calculator, 60, divide by 365, and you get 0.164 years. Here's a reality check for you. 60 days is a lot less than a year, right? So you should be getting a number that is less than 1. You should be getting a decimal. If you get something bigger than 1, you messed up. 300, you might have done 365 divided by 60. That's going to give you 5-6 years, something like that. So we know that 60 days is a short period of time. It had better be less than 1 year. So that's how you can check yourself. All right. Now, once you've got the star mass and once you've got the orbital period in years, you're ready to go. You can put it in your Kepler's third law tool and you can figure out what is the sum of major axis. So I want you to pause the video, do that right now, then we're going to come back and go over it. Pause the video now. All right, so did you get it? Let's look at the tool. Let's see how we fill it in. So remember, it's MP squared raised to the 0.33333333 until you get bored. Yeah, you could do it to the 1/3, but if you do it that way, make sure you put those 1/3 in parentheses. And for me, that's too many keystrokes. I'm too lazy to do that. So I do 0.3333333333. Okay, I'm bored. And hit equals. All right, so our M is 1.36. Our P is 0.164, and remember we square that. So you do 1.36 times 0.164 squared, hit equals, always. And then raise to the 0.333333333333333333. Oh, yeah, okay, I'm bored. And then hit equals. And you should get 0.332 AU. That's roughly the distance of Mercury. So here we've got a planet that is actually very close to its star. It's about 0.32. Unless this is a very cool star, and we know from a main sequence star, if it's bigger than the sun, it's probably not a cool star. This one's probably not going to be habitable. Do you see that? Because we've got a star that's bigger and therefore hotter than our own star, and we've got a planet that's very, very close. It's like the distance of Mercury. So chances are this one's dead to you. So let's use that logic then. That same logic that we just went through. You can do a lot of this without doing any math whatsoever. You've got 500 stars to look at. Do you really want to go through every single one of them? So let's think about how we can eliminate. We talked about, if it's not a main sequence star, you're out, you're dead. All right, well, what about, let's suppose I have a sun-like star, and I've got a planet that is 20 AU away. Remember, Earth is 1 AU. And this sun-like star means that it's basically the same mass and temperature as our own star. So what do you think? If it's 20 AU away, that's like Neptune's distance. Do you think it's going to be too hot, too cold, or maybe good? Yeah, that one's going to be way too cold. So it's too far away. So that one probably you're not even going to want to worry about. So what if it has a planet? If that planet is that far away, it's not worth your time. You're looking for that one habitable world. It's dead to you. Kick it out. Move on. All right. What if it is 1 AU from a sun-like star? Well, that's maybe good, right? Because Earth is 1 AU and we have a sun-like star and we're habitable. Does not mean it's habitable. Keep that in mind. Just because it's at 1 AU does not mean it's habitable, but it does mean that, it's something I want to look at. And so you go back and you continue on with your analysis from that one. How about if it's 0.25 AU from a sun-like star? So here's our sun-like star, and now instead of being at Earth distance, it's this far away. Too hot, too cold, or maybe good. Yeah, that one's going to be way too hot. It's much too close. That's even closer than Mercury's distance. So no chance. All right, now here we have a star. It's 0.25, so it's very close, but the star is only half the size of the sun. So if it's half the size, what does that tell you about its temperature? Is that star hotter or cooler than the sun, based on what you know about star classes? Okay, it's going to be actually quite a bit cooler. And this planet is 0.25. What do you think? Too hot, too cold, or maybe good? Well, you're going to probably have to look at it, but this one's maybe good, right? We've got a dim star. So in order for the planet to be habitable, that planet has to be very close to the star. How close? Well, we don't know. We got to do the math. But that's the case where we need the details. But in this case, we've got a star that's pretty dim, pretty cool, and we've got a planet that's pretty close. So maybe good, maybe not, but it's worth carrying on. Now, looking at the last one, now we've got a 4 solar mass star. So this star is 4 times the size of the sun. What does that tell you about the temperature of that star, based on what you know about star classes? So this is a crazy, crazy hot star, really, really big and bright. So if I have a planet here, obviously it's dead, right? If I have a planet at Earth's distance at 1 AU, it's dead for sure. What if it's at 20 AU? Well, what do you think? We've got a hot star. It better be a long way away. It is a long way away. Is it right? Well, I don't know, but we could go with maybe good. We certainly can't eliminate it the way we can with these. So you see that using these kind of techniques can eliminate some, but not all of the stars. Sometimes you need to know the details. When you need to know the details, that's when you go to the math, not before. Don't let going to the math be your first line of attack. Always, always, always be lazy. Think about it, understand the science, and that will help you to eliminate. You've probably knocked it down from 500 to 200 stars just using these kind of logic things that we're talking about here. One last note, just a side note, this doesn't come into play with your final project, because for your final project, we're going to assume that all of the stars have planets that are aligned. Their solar system is aligned to us. So, this is our solar system, this is theirs. But in reality, out in the real world, these star systems have all orientations. They're not all just aligned. Now think about this one right here. If I had a star system, let's say we're here, and let's say I'm looking at this star system here, and the planet goes like this. Is that planet ever going to pass in front of its star relative to us? No. So this planet is absolutely invisible to us using the transit method. We're not going to be able to determine anything about its size using the transit method. So now if we were down here, if you look down below the screen, if we were looking at this way, then yeah, it would be passing in front of it. Use that spatial transformation to think about it. So we can only think about the stars that have planets going around like this. But even using this technique, we have managed to find almost 5,000 planets. And so since we can only get the small percentage that happen to be lined up to us, we know that the number of planets out there is actually much, much larger than that. So that's a good thing. That's a good sign. Even though we can't detect these, we know that they have to be out there, because we know that all solar systems, there's no reason for them to be all lined up. They're all going to be in these random orientations. So if even a small fraction has this many planets, chances are practically all of them do. All right, so this is Kepler's laws. I want you to do obviously the planet size one, and then work it out in Canvas, and then upload it, and we'll be good to go. So now you know how to find the mass or the size of the planet anytime that you need to. Now remember, we're talking about size. We're talking about the diameter of the planet, how much physical size it has, how much it's blocking the light from that star. So this is going to be real important because not only does that tell you, okay, is this roughly Earth size or is it roughly Jupiter or Saturn size? It also then we can use that to get the distance of the planet from the star by determining the orbital period that it comes on, how many days there are between those dips. But if I want to figure out if this is actually a Jupiter-sized planet or an Earth-sized planet, a terrestrial planet that critters can walk on, or is it going to be a gas giant that nobody's going to be able to walk on? How do I do that? Because remember, one of the planets we found was actually 2.5 times the size of Earth. Well, okay, that's not a gas giant, but that's actually a really big planet. What if I had just a really small gassy planet? Or I had a really super huge icy planet? Or terrestrial planet that was ultra huge, something like that. How do I tell the difference? Well, I need to do that. I need to find the density of the planet. Density we're going to talk about later, but that's basically how compact it is. Iron is more dense than water, for example. So we can determine what the planet's made out of based on its density. But in order to find the density, not only do I have to know the size of the planet, I have to know the mass of the planet. So next week we're gonna be talking about how to find the mass. That's actually how much matter is there. And then we'll know how compressed it is, which will tell us if it's rock or gas. So to do that, we've got a couple of things we've got to build up to. We're going to talk about how to find the velocity, and then we'll use that to actually figure out the mass. So we'll see you next week.